So at this point, I'm assuming you've already read the textbook on this section about stars and bars, but briefly the idea behind a stars and bars argument is whenever you have one of these distribution problems where we're talking about solutions to a linear equation with positive integers, instead of encoding your solution as ordered quadruple like 2, 0, 2, 1, the standard approach is to make a stars and bars chart where you have, because we see that we have the first coordinate is 2, we have 2 stars followed by a bar. The bar tells you to switch to the next coordinate. And because the next coordinate is 0, we have no stars between these 2 bars. And since the next coordinate is 2, we have 2 stars. And finally, since the last coordinate is 1, we have 1 star. And so that's a way to go from a quadruple to a stars and bars chart. Likewise, you can go the other direction, given a collection of stars and bars. Say this one. What can we say about it? Well, let's add one more star. Well, we read left to right, we see 3 stars and then a bar, no stars and then a bar, 1 star and then a bar, and then 1 star. And so these are both solutions to the equation a plus b plus c plus d equals 5. And you can do this in general. And so stars and bars pop up for 3 different types of problems. The first type of problem is exactly the one we've been talking about. You're talking about the number of integer solutions to one linear equation, x1 through xk equals some constant integer n. And one way to solve this counting problem is to replace the first coordinate with a1 stars, the second coordinate with a2 stars, with a bar between them, then another bar and a3 stars, and so on up to a, that should be an ak. And the reason why you'd want to do this is it gives you one way to solve this counting problem, because these two things are equivalent. Given one of these star and bar charts, you read left to right how many stars before the first bar, that's your first coordinate. The next number of stars is the second coordinate, and so on and so forth, where whenever you see no stars between 2 bars, you have 0. And so what do we have? We have a sequence of stars and bars. How many symbols are appearing in this sequence? N plus k minus 1. N is the positive integer, there's n stars, and there's k minus 1 bars, corresponding to the fact that we see that we've partitioned into k groups. And so we have n plus k minus 1 symbols, and we have to choose k minus 1 of them to be bars. The reason for it being k minus 1 is because you're breaking up into k groups, and you only need k minus 1 bars to do that. And so we would need n stars and k minus 1 bars, and so the number of such sequences is a binomial coefficient. You could pretend that these are zeros and these are ones if you want, and so you get n plus k minus 1, choose k minus 1, taking the number of possible symbols in your sequence and picking the bars and making the rest stars. By symmetry of binomial coefficients, it's also this equation, which could be viewed as picking the stars. And so the answer to these distribution problems is actually a binomial coefficient. It's just not n choose k, it's something slightly more complicated. The second common type of problem where stars and bars pops up is when you're distributing n identical objects to k distinct people or bins. So this is just like the Rubik's Cube example. Distributing Rubik's Cubes to people or cookies to children is an example also given in the book. And it turns out you could do stars and bars. Another approach I like to think of is to actually connect it directly into solving linear equations. You let xi be the number of objects the ith person receives, where you've named your people 1 through k. And then you see that the number of ways you can distribute the identical objects to the people is just the number of solutions to this equation. And as we already saw, that's this binomial coefficient. You could also do it using a star and bar chart, where the number of stars in the between 2 bins is counting the number of objects you gave to that person. and it's still the same answer. It's worth pointing out by identical, the whole point is that you can't distinguish between the objects. So if you give me 3 cookies, and if you give one person 3 cookies and another 2, there's really no way to distinguish between the 3 cookies. The third type of problem, which pops up as one of the homework exercises in the book, is called a multiset. So this is the type of counting problem that pops up when you're taking n marbles out of a bag where you have k different colors. So you're taking a bunch of things out of a container, the things have different types, but you don't allow ordering. But you have infinitely many of each type, so you're allowed repeats. So for instance, if I had 3 colors, red, green, and blue, and 5 marbles, I could be talking about the number of ways to pick out 5 marbles out of 3 different types. And so you see, you could get, say, all red, 2 red, a green, and 2 blues. Yes, I suddenly realized that I didn't get the colors to match, but this is the idea. And how many ways can you solve this type of problem? Remember, the order doesn't matter. Well, you could do a similar type of trick. You could let xi be the number of marbles of a given color. And then the number of ways to solve this problem is, again, the number of solutions to this equation. And so, again, it's this binomial coefficient. Because the way the textbook likes to view this is, if I let R be the first color, then I see 2 of the first color, 1 of the second color, and 2 of the last color. And so again, I see I get a star and bar chart. And so I get binomial coefficients. So as a follow-up, a type of problem you often see in this course is a related distribution problem. Suppose I want to give 7 cubes to 4 kids, but I want each kid to get at least 1. So I already mentioned earlier that this is the solution to a linear equation, a plus b plus c plus d equals 7, where these are the number of cubes you give to each kid. Remember, you should be able to tell the 4 kids apart. No identical twins here. With the added restriction that each is at least 1. And one way to solve this problem is to hand out 1 to each kid first. So to do this linear transformation, and then distribute the remaining 3. So when you do this linear shift to each of the variables, you're decreasing the right-hand side by exactly 4. So you're just solving this equation. And you can view this equation as figuring out how many more you're going to give each kid after the 1 they're guaranteed to receive. And we already know how to solve this problem. It's a binomial coefficient by doing stars and bars. But you can generalize. I could replace 7 with any positive integer n. You're distributing n objects to k people, and you're requiring everyone to get at least 1. And in general, if you follow this logic, this is the answer you will get. Give everybody at least 1 first, so you have n minus k objects left. And then with those remaining n minus k objects, distribute them. And this is the number of ways to do that. And because you already gave 1 to each person first, you already meet this restriction. And so this is the number. Now, as a summary, it's worth pointing out that at this point in the course, we've seen a bunch of counting problems that are closely related, so I thought I'd summarize them. Sometimes in counting problems, you have a number of options, so like the number of toppings on a pizza or the number of shirts, and you're making a certain number of choices. So I'm going to let that be n and k for these formulas. Now, suppose that your choices are ordered, so you make the choices in some sort of sequence, but you're allowed to make the same option, pick the same option more than once. Then we've already seen that this is n to the k, because the reason why is we're ordered, so you have to make a sequence of choices, and you're making k of them, and for each choice, you're allowed to pick all n possible options. So n for the first one, n for the second, n for the third, and the product of n k times is n to the k. This is an example of the generalized multiplication principle. One natural restriction we've also looked at is what happens if we have ordered sequences, but we require distinct entries. No repetition is allowed. And we've already seen in class that after you've made the first choice, you've excluded one option from the second choice, so you have n minus 1 remaining options. And after you made the first two choices, you have n minus 2 remaining options for the third choice, and so on and so forth, all the way down to the last choice. And the last choice, you have n minus parentheses k minus 1 options, so you have this many options left. And as we've seen, this can also be written as n factorial over n minus k factorial. It's worth pointing out the book sometimes uses this notation for it, and I think in class I used that notation for it. And today we discuss what happens when you're dealing with unordered repetition. So you're allowed to pick the same option multiple times, but you no longer care about the ordering. You just care about what you actually picked. So this pops up when you're ordering food at a restaurant. People can order, more than one person can order the same thing, but certainly it doesn't matter what order you order the food in. And so what we see is then we're studying the stars and bars type of argument or linear options. It no longer matters that what your options are. It just matters how many times you take each option. So you do a star and bar chart. You'd count the number of ways you pick the first option, right? And then the number of times you pick the second option, and so on. And then you'd see that, well, there were exactly n minus 1 bars because you made n possible options and you've made k total choices, and so that's how you get this binomial coefficient. And finally, if you do unordered and no repetition, you're just choosing a subset because you can't pick the same thing more than once. So once you pick an element, you have to pick something else, and order doesn't matter, so it is a subset of size k, and so you get n choose k.